Characterization of FFLGN by Raman spectroscopy. The Raman spectra of FFLGN, like graphene, have G and D bands. The first order of scattering of the AE2G phonon of sp2 carbon atoms G, the band is reflected around 1500 centimeters and also occurs due to stretching the CC bond in the basal plane, which is a characteristic of all sp2 hybridized carbon materials, and the D band appears in zone of 1200 and 1400 and indicates certain amount of disorder, defect, disorder of edge in the carbon structures. D band and J bands have certain differences compared to graphite and graphene. In FFLGN and the D band is wider and more intense, while the G band is suppressed and significantly broadened and sometimes slightly mixed to high frequencies. This shift may be due to the doping effects, with the result that doping will affect the mixing of the G band. DG and 2D Raman scattering bands the basis of characterization of the reduced FFLGN and determining the density of defects. In work, it is given that with increasing degree of functionalization, wide DG and 2D bands are expected. Also in this paper, it is considered that the degree of functionalization cannot be determined by Raman spectroscopy. Another issue in the Raman spectroscopy of FFLGN and reduced FFLGN is the change in spectra after reduction. The D band in FFLGN is mainly due to chemical functionalization and the expanded quantity of sp3C atoms, also structural defects inside the carbon skeleton. Functional groups are removed by reducing from p surfaces and from structural defects such as vacancies or rebuilt carbon structures. 5-membered or 7-membered rings dominated. As described above, the D band in graphene can be caused by structural defects or functional additions, as in FFLGN. Thus, by removing and adding functional groups, carbon integrity can be studied to determine the relative content of defects in the sp2 carbon lattice. The most convenient measure is the ratio between the intensity ID-Ig. The ID and Ig ratio in the FFLGN is more than graphene or graphite, where the D band is often indistinguishably from the background and the ID-Ig is over order of 0.01. Since the disorder in the graphene lattice begins to increase with a low density defect, the ID-Ig ratio also increases at first, with a further increase in the density of defects ultimately lead to the loss of carbon lattice. The ID-Ig ratio begins to decrease due to non-linear dumping of all the peaks of Raman scattering when the material begins to turn into amorphous carbon. In the low density mode, ID-Ig can be approximated by an empirical formula linking the relation to the distance between the two adjacent defects, ID-Ig and CLA lambda, where lambda is excitation wavelength of Raman scattering and lambda is an empirical parameters, 102 nanometers for the excitation wavelength, lambda 540 nanometers. For edge defects, another formulas. The Tunstra-Cohen ratio is more appropriate. Here is lambda 2.4 nanometers and lambda is the Wi-Fi